Everybody, and so welcome to the fourth day of this workshop on random grass and trees. And so our first speaker this morning is Nicola Kistler, who'll be telling us about a multi-scale refinement of the second moment method.
Okay, thank you for the invitation to this great conference. I'll be talking about work which I've been doing with Louis-Pierre Arguin and David Bailius. They are both here in the audience, and then Anton Bouvier, and more recently with a PhD student in Frankfurt, Mario Schmidt. And so I put this sentence, much influenced by Bolthausen. It's as I said, I'm trying to convey a point of view, and it's very much influenced by attempts to say something about spin glasses, which I've been trying to do with Erwin Bolthausen. The closer I get to the end, the stronger the influence. So here's the outline. I will introduce a couple of models, and I'll be interested in the extremes of these random fields. The first one is a paradigm, is the Gaussian hierarchical field, and I'll briefly state the problem of cover times. The famous, celebrated by now Gaussian free field. I won't say anything about the Riemann zeta function and characteristic polynomials. I think this will be a major part of Louis-Pierre's talk. And then I will work out this multi-scale refinement of the second moment method. I'll do it in detail for the hierarchical field, and then with less details for the cover time. And I'll briefly discuss the limiting picture which emerges, and then I'll conclude with something which I find very, very fascinating, the problem of finding scales. In any case, so start. So the Gaussian hierarchical field, I guess it's a well-known object. What you do is you take a binary tree of depth n. I will refer to the depths as scales. And then what you can do, you attach, it's the directed polymer and Cayley trees. You attach independent Gaussian random variables to the edges. So this is x sigma 1, x sigma 1, sigma 2, all the way down to the leaves. And then what you get is a Gaussian field. How do you construct it? You just sum along the paths leading from the root to any given leaf, and this gives you an energy. And the collection of this x labeled by the leaves is then a correlated Gaussian field. And the question I'll be asking, what is the maximum of this field? Okay, well, here's another problem, the cover time of the two-dimensional torus. I denote by c epsilon the time for Brownian motion to come within distance epsilon from each point. So here's some simulation by David. So what you see, the purple thing here is the trace of Brownian motion. So it doesn't really matter by scaling. You can take a torus of size length 1, and what you see is the trace of Brownian motion. And then, of course, if you don't run it for long, then Brownian motion is essentially far away from every point of the torus. But then you see, if you wait longer and longer, then Brownian motion starts to fill out this torus. Here, if you wait up to time 3.7, there still is a ball of radius 0.06 which has not been hit. That means that 0.06 cover time has not happened because Brownian motion is still far away from the center of the ball. Then you wait longer, and you see this ball disappears, and there is still a tiny ball of radius 0.02. So the question we would like to answer is this: how long does it take to cover the torus if you let epsilon go to 0? So this is exactly as covering the torus by a Wiener sausage of radius epsilon. Okay, what about the Gaussian free field on Z2, the discrete GFF? Okay, so you take a box of size n, and then you run a simple random walk on it, and you kill it when you hit the boundary. Of course, you can associate to this the green function, and the green function is positive, and it has good properties. And it can be seen as the covariance of a Gaussian field. And that's a Gaussian free field. We define the Gaussian free field indexed by the sides of this box as the center Gaussian field with covariance given by the green function of the random walk killed upon hitting the boundary. Okay, this is a famous model of a random surface with lots of interesting properties. And also in this case, you can ask what is the maximum of this field. If you let the size of the box, this is a 10 by 10 box, if you let it go to infinity, how large is the highest peak? Or what about the second largest, and all these kind of questions. So, so these are the models that I'm interested in, and I'll come now to this multi-scale refinement. So it's simple. I hope to convey this feeling. It's a simple procedure. It's based on a couple of steps, 3 steps, in fact. So in lack of better words, I call this matching multi-scale Markov and truncated Pelliz-Sigmund. And I'll work it out now for the hierarchical field. That's the representative of a certain universality class. Some notation here. If you're given this binary tree with these energies attached to the leaves, you can consider, if you give me a path from the root to the leaf, I can see the partial sums as a process indexed by the depth, by the scale, and I'll refer to this as a profile. Of course, by construction, all these random variables are Gaussian, independent Gaussian. It's a Gaussian random walk. Now, here's the absolutely fundamental feature of this hierarchical field. If you take any 2 leaves, then there is a common branch up to which point the profiles coincide, and then by construction, what happens below this scale, it's just independent, completely independent random variables. So by this is what I mean when I say there is an exact tree structure. Of course, there is a tree, but the important thing is this certain decoupling. In all the other models, there won't be any exact tree structure, but an approximate tree structure which is good enough to carry out a certain analysis. Okay, so the question was, I want to study the maximum of this Gaussian field, and I have these 3 steps. This Pavlov reflexes, this matching, this multi-scale Markov, and the truncated Pelliz-Sigmund. And here's the first thing: the matching to first moment, to leading order of the first moment. So I want to study the maximum. So it sounds like a good idea to count the number of configurations, the expected number of configurations, which reach a certain height x. Now, of course, by linearity, this is just 2 to the n times the probability that one configuration reaches this height. Okay, this is a great function of Gaussian. And here's the matching. I'll require that this is of order 1, and then I solve with respect to x. And then you see that this is of order 1 for x, which grows linearly with the size of the system, with the depth of the tree. Okay, there is a constant, this is square root 2 log 2. It's not really so important. And so this is the matching. I just match the first moment to unity. Now you see, this is already some piece of information, because by Borel-Cantelli you can prove that if x is much larger than this threshold where everything is of order 1, well, then you will find no configurations at these heights. So in lack of better ideas, maybe you can take this BCN as a candidate for the maximum of the field. Okay, well, can we improve this? And the answer is yes. So, and here's another Pavlov reflex. Take this BCN and then consider the linear interpolation. Then you can take your a realization of your field, and you shift it. You shift this linear interpolation by something of order much smaller than n, say something like 100 log n. The factor 100 doesn't have any meaning. It's just you choose things so that things work. And in doing so, you construct a barrier. And why is this a barrier? Because by Markov inequality, just the simplest thing you can do is you can prove that by Markov inequality that the probability that there is a profile which crosses this barrier at a given level k vanishes. Okay, this is just Markov inequality and Gaussian estimates. On the other hand, you can also do the following. You can sum up over given the choice of your barrier, you can sum up over the scales, and this is the reason why I call it this multi-scale Markov. You still see that the sum of this probability goes to 0. But this is an important observation because it implies that no profile goes above the barrier. And this is, and somehow it's okay. It's a bit by hand waving, but this is the way we break the self-similarity of the field. It will come out, hopefully it'll become clear what I mean by this. But this information is absolutely fundamental because I can use it for a refined analysis, namely, I've been able I have a good candidate. I have a candidate for the leading order of the maximum by matching to leading order. But now the question is, do we have some second order correction? So what I can do is to consider now the number of particles which configuration will reach these heights BCN, so what comes out of first moment leading order analysis. And then I'm wondering, is there a lower order correction? Well, in any case, I know by the previous analysis that nobody gets above the barrier. So let's use this a priori information and write it out. I mean, this is 2 to the n configuration, then the probability that one configuration does this. So this is another Pavlov reflex. You should always condition in these models on the terminal event. So what I get is this exact expression. And now I'm wondering, okay, you don't see much colors, but okay, so the question is now, what is this probability that you stay below the barrier condition on the terminal event? Now by construction, I'm considering now just one profile. The profile has to reach these heights, but it also has to stay below the barrier. Now by construction, this is simply a Brownian bridge, okay, discrete time Brownian bridge with a drift because it has to reach these heights, and it also has to stay below this barrier. Now what you can do, this thing is invariant under rotation, so you can rotate it, and what you get is a Brownian bridge, a classical Brownian bridge. It starts and ends in 0 of length n, and it is not allowed to touch this barrier. Now this is absolutely fundamental observation. This barrier is of order log n. But Brownian bridge is square root of fluctuations. So if you're not allowed to touch it, what will you do? Well, it's kind of natural to believe, well, Brownian bridge will do something like this. It will go down. In order to make room for these fluctuations, it will go down. It will follow essentially minus the absolute value of its typical path. So this is something which is reminiscent of entropic repulsion, which happens in the statistical mechanics of random surfaces. It's inherent. It's in the model. It's not that I'm requiring this to happen. The model itself does it. It's probably a bad choice of words, but we couldn't find anything better. Okay. So it goes down by something of square root of n. This is a typical path, but simply in the negative, in order not to touch this blue line. But then you can rotate and get the real picture. Namely, if you have somebody reaching these heights, I still don't know if somebody reaches these heights, but if they do, well, the path must do something like this. Okay, this at the beginning and at the end is always a bit tricky to say something, but for most of its time, the Brownian bridge will follow this kind of path. And now we know what this probability is. Well, it's a probability of a Brownian bridge which has to stay below 0 essentially. And this is it's well known. The probability is inversely proportional to the length of the bridge, so it's essentially 1 over n. Okay, so we have this information now. Okay, what about the first 2 terms? Okay, this is easy. Just plug in the definition of the Gaussian, and you see we have now this kind of correction. So this is normalization of the Gaussian, and then this is the density of the Gaussians. They give a contribution of n to the 3/2. And here's the matching. I'll set this equal to 1, okay? And then I will solve with respect to the lower orders. And then if you solve with respect to this, you see that the second order correction is logarithmic, and it's okay. This famous 3/2, which was first identified by Bramson in branch Brownian motion. Okay, what do we get? Is that this Mn, this BCN, which comes out of matching to leading order, and this correction, which comes out from matching in this entropic repulsion, is certainly an upper bound. You cannot do anything better than this because, okay, this is the last, this value here is the last value for which this is of order 1. If I choose something higher, everything will go down to 0, and then by Borel can tell you, see, nobody reaches these heights, okay? Now, of course, we would like to say something more. Is it also a lower bound? Well, if you want to prove that something is a lower bound, we don't have much. We have to, this extremely flexible and universal Paley sigma inequality. But if you try to do it in a naive way, it will not work because of correlation essentially. But we have some a priori information which we will use as a truncation. Namely, we'll consider only profiles which are below this square root barrier, because we know nobody goes above. If you want to reach these heights, you have to do something like this. And then what we will do is, okay, the probability that there is somebody at these heights is certainly larger than the probability that somebody reaches these heights and stays below the barrier, just restricting the event. And now I apply Paley-Zygmunt. So this is, the probability is greater than the first moment square divided by the second moment. Now the first moment, it's what we studied on the previous slide. The question is now, what happens to this second moment? Well, you see, I'm counting the number of configurations squared. So it's a square of a sum, so you can write it out and see and rearrange. And then you will see that you get the first moment square plus 2 jumps. What do I mean by 2 jumps? Well, it's a situation like this, that somebody contributes with two offspring to this maximum. But you see, we are starting low. And then it turns out that this is too costly. You cannot make 2 jumps. You can make at most 1 jump. In other terms, this event, 2 jumps, is a lower order. But you see, now we are in business, because we have the first moment square divided by the first moment square plus lower orders. And then, not surprisingly, this will go to 1. Okay, there are lots of technicalities behind this, but this is the main idea how to tackle this. So this Mn is indeed the level of the maximum. Okay, here's the full picture that has emerged in about 30 years about the extremes of the hierarchical field. First of all, the Mn is indeed the level of the maximum of the field. If you shift the maximum by this quantity, it will converge to a random shift of the Gumbel distribution. And then we know what the full extremal process, so we know the statistics of the second largest, third largest, and so on. It's a Poisson cluster process. It's a tricky object. It's a fractal. There are many names attached to this pretty detailed description of the limiting, the weak limits of the extreme values of the hierarchical field. Okay, this is something which we studied very recently. It was about trying to interpolate from the IID setting to the branch random walk in order to get some insights about this tricky fractal of the extremal process of branch random walks. It was kind of a disappointment. It doesn't work, but you still get something interesting, somehow interesting. So the idea is to take a model which interpolates. You see, the number of scales gives me some information about the amount of correlations which are in this field. Now, by Slepian lemma, for instance, you can expect that if you increase the amount of correlation, then the maximum should go down. Now, how can we increase the amount of correlations? Well, we can choose models with a growing number of scales. So what we do is we take a parameter alpha, and we consider a model which has n to the alpha scales. So here are 3 examples. Now, if you choose alpha equal to 0, you get the famous random energy model by Derrida. You have just a single scale, and everything is independent. Now, if you take alpha equal to 1, you have this hierarchical field. You have this binary tree. And of course, I mean, if you take alpha between 0 and 1, you have something which interpolates between the least correlated and the most correlated within this class. Now here's something that Mario Schmidt, as a PhD student in Frankfurt, worked out. So the maximum, you can ask, what is the maximum of the field? Well, it turns out that the maximum to leading order is exactly as in the hierarchical field or in the random energy model. All these models have to leading order the same value. What happens, something interesting is happening only at the level of the logarithmic correction. You see, you have this factor 1 plus 2 alpha, which interpolates from 1 to 3. 1, if you choose alpha equal to 0, is the logarithmic correction of the random energy model. If you choose alpha equal to 1, you get the logarithmic correction, this Bramson correction. And then you can get models which have any kind of interpolation between 1 and 3. The disappointment was this, that it turns out that as long as alpha is less than 1, the extremal process is always Poisson. So this was not something we expected. We were probably being too naive to believe that this model can interpolate at the level of the extremal process. Okay, it's kind of natural to believe that if you want to have something more interesting about the extremal process, you should choose also alpha, which tends to 1 with n. So depending on n, but I don't know. I mean, it might be tricky to analyze in this generality all these models, but it's something we stopped doing. Okay, so this was the hierarchical field. I'll move on now to the cover time in the torus. So this was C epsilon was the time for Brownian motion to come within distance epsilon from each point of the torus. And we are interested in the small epsilon limit of this quantity. In order to get a handle, it's a good idea to consider the field of occupation time. So what you do, you tile your torus with balls of a certain radius, and you consider the amount of time that Brownian motion is spent in these balls. Okay, so this is a beautiful simulation by David, and what you see is you see there are these blue seas with these purple islands, and there Brownian motion spends lots of time. On the other hand, there are these yellow pockets and orange islands, and there Brownian motion spends little or no time at all. So you've started with a tiling with a certain radius. If you still see orange, covering has not happened, because there Brownian motion hasn't visited these islands. So what you can do is the following. So you can tile the torus with balls of radius epsilon, simplify life, make them non-overlapping, so you will have about e to the minus 2 balls. And here's the observation. If there is a ball with zero occupation, then covering has not happened, because Brownian motion, as the trace of Brownian motion, is at least epsilon steps far away from the center of this ball. Okay, so let's use this and count the number of balls with zero occupation at time t. So I run it up to time t, and I see how many balls have zero occupation. Well, I have e to the minus 2 balls, and okay, probably the one ball has zero occupation. If one ball has zero occupation, okay, these heating times are essentially exponentially distributed with this mean. And here's the matching. I'll match this one to unity, and I solve with respect to t. Now, the solution of this equation t, which solves this equation, is certainly an upper bound to the cover time, because if you wait longer, then the whole thing will go to 0, so you have no balls with zero occupation, so covering has happened. Well, it turns out it's also a lower bound. And this is something due to Dembo, Perez, Rosen, and Zaitouni 10 years ago. So the leading order of the cover time comes out of this first moment computation, which is kind of surprising. I'll come back to this later on. So if you want to prove a lower bound, again, maybe not surprisingly, we don't have so much. We have Paley Sigmund. Of course, also here it's a highly correlated random field, so you better look for a truncation. So in fact, this is essentially the proof by Demo, Perez, Rosen, and Zaitouni. It's by truncating the second moment, and you exploit the correlation structure in the field of occupation times. So there are two words which I wanted to briefly discuss. First, the correlation structure. Well, it's based on this idea. You can imagine, I believe you agree with this, if two balls are very close, there shouldn't be any reason why they have extremely different occupation times. Essentially, if they are close, you should get the same amount of occupation. On the other hand, by Markovianity, if the balls are far apart, then the occupation time should be essentially independent. But this is absolutely an absolutely fundamental observation, because it means that there is an approximate tree structure behind this problem of cover times. And that would be absolutely fundamental for the rigorous analysis. Now, what about the second word is this one? What about the truncation? Well, if you have a truncation, you should have a strategy. You should understand something about how things happen. And the strategy should answer this question: how do you avoid balls for long? Now, it is a kind of a natural idea. If you have a ball with zero occupation time, well, it's kind of natural to expect that this ball will be surrounded by larger balls. So this region is within a region with low occupation time. In other words, you should look for a situation like this, that Brownian motion, the two-dimensional planar Brownian motion, just avoids certain regions. Okay. Now, so this is summarizing. This is the theorem by Demo, Perez, Rosen, and Zaitouni. And there is something curious about it, just as in the hierarchical field. The leading order came out from a first moment computation. So it's exactly if things were independent. Now you can wonder, is there a lower, or is there a correction to this quantity? And I mentioned briefly why this is an interesting question. Now, the second order correction, which you cannot get from a first moment computation, was improved recently by Jian Ding, who proved that if there is a correction, it is a most of a log-log order. Now, why is this an interesting question? Because, of course, you can ask the same question of covering a torus in 3 and higher dimension. But there, things are radically different, it turns out. Namely, in 3 and higher dimension, things behave as if you were covering the torus by throwing independent balls. More precisely, there are no lower order correction. The fluctuation of the cover time are given by the Gumbel distribution, and the full limiting extremal process, the collection of points which regions which are hit the latest, is given by Poisson point process, and this is due to this. David Bellius and then Olander and Goodman proved this full limiting picture. And of course, you can imagine what's the difference between 2 and 3 and higher dimension. In 2 dimension, you have this local recurrency which builds in correlation among the field of occupation time. In 3 and higher dimension, because of transients, at some point you will not come back to the balls you visited. So this decouples somehow the field, making this much easier than the 2-dimensional case. In any case, so we would like to say something about, do we really have log-log corrections? Can we say something about fluctuation, about the limiting picture? So the idea to tackle this problem is to consider the multiple scales in the field of occupation times. What I'm doing is I'm plotting, again, I'm tiling the torus. I start with macroscopic balls, and I'm considering, and I'm looking at the amount of time that Brownian motion run up to time t spends within these balls. And we see with macroscopic balls, well, it's all green. It's essentially everybody gets 30% of the amount of time, which is something you should expect, at least at this level. But then I can do the following. I can shrink the balls and do the same, record the amount of time you spend in these balls. And you see, if I keep doing this, there is lots of structure which comes out. Okay, you can do it all the way down to your scale epsilon, to the microscopic scale. And in order to get a handle on what's going on, well, we use this idea. So what we do is the following: you fix one ball, one point in the torus. You run Brownian motion up to time t, and what I will do now is to plot the occupation time of the balls surrounding this center at this point x, but I will plot it as a function of the radius of the balls. Okay, so this is the occupation time of the balls around this concentric balls around this point x. Okay, I have to rescale it by the area of the balls, and to get something nice, I should get the square root. So what I do is the following. So I start with the macroscopic ball. Imagine that this is a macroscopic ball which covers the whole torus. You've run Brownian motion up to time t, so the occupation time of this ball will be t essentially. So I will start at square root of t, because okay, pi r squared is going to be essentially 1. Then what I do is I shrink the ball and I record the occupation time. Then I shrink it and record, and shrink it and record, all the way down to scale epsilon. Now what you see is, okay, what we get is, of course, it's a random process. Turns out to be a Bessel zero process, which, for what I'm saying, behaves essentially as a Brownian motion. And this was, however, this was a profile of a generic point, a generic ball with which you tile your torus. But we are interested in balls with zero occupation. So if you have zero occupation, the process should do something like this. But we started with the Bessel zero process. You condition it to hit 0 at scale epsilon, so it's going to be a Bessel bridge. And what you can do, okay, first this is how the Pavlov reflex. If this linear interpolation now turns out to be again the mean of the process conditioned to die out. And what you can do again, as in the hierarchical field, you can shift this by a small amount. We'll not shift it upwards, we'll shift it downwards in this case by something small. I will give you, no, I think I will not give you any details about this, but I'll give you some more quantitative things a bit later on. In any case, you can shift this down, and what you do, you construct a barrier. And why is it a barrier? Because, okay, we now have this multi-scale picture, just shrinking the radii of the ball. And then it turns out that by multi-scale marker, if you sum up and the probability that you cross at some point this barrier, well, you see that it goes to 0. So essentially it says that no profile gets below the barrier. But this, remember, this was some sort of Brownian bridge with lots of which big fluctuation. And then if you're not allowed to do this, what can you do? Well, you go airborne in this case. It's again the same phenomenon of entropic repulsion. To avoid hitting this because of the fluctuation, you just go up. Okay, so the probability of this event to avoid this barrier in end and 0 is 1 over the length of the bridge. I haven't told you how to choose scales, but you should choose them geometrically shrinking, and then you get that this is two leading orders, 1 over log of epsilon. Okay, this is also another important observation because nobody can you see, nobody can get below this barrier, and we will use this information for the matching to lower orders. Again, I count the number of balls with 0 occupation, and that also avoid the barriers. Nobody does not avoid the barrier, so I can also plug in this information. And what is this? Well, the first two terms, and then I condition on the terminal event. I'm just following exactly the steps in the hierarchical case. I plug in the numbers that we have identified, the quantities that we have identified, and then I'll match it to unity. Okay, and then I solve with respect to t. Now you see, we have gained compared to the macroscopic analysis this log-log correction, which comes from the fact that you have to avoid this barrier. Now this is certainly an upper bound, because if I wait longer, then the whole thing will go to 0. So by Borel-Cantelli, you will have no balls with 0 occupation. But it turns out that this bound is tight. So this log-log correction is indeed the second order correction to the cover times. Of course, again, if you want to prove that it's a lower bound, we know it's an upper bound. How to tackle the thing from the other direction? Well, it's going to be truncated Paley segment. So what do I mean by this? I'll rush through it. So take a ball with 0 occupation time. We know we are considering this profile process, and we know that the occupation times at higher scale should look something like this. I mean, this comes out from this entropic repulsion, and then we will follow exactly the steps in the hierarchical case. The probability that you have a ball with 0 occupation before this epsilon identified in the previous slide is certainly greater than the probability, and then where you add the condition that each profile is above the barrier, and then you apply Paley segment. So you get the first moment squared divided by second moment. Again, the only thing we have to analyze here is the second moment. So write it out. You will see it's the first moment square plus 2 jumps. So what is 2 jumps in this case? Well, it means that you have 2 balls with 0 occupation at your epsilon scale. At the level of the profile process, this was the absolutely crucial observation by Dembo, Perez, Rosen, Zaitouni. You have an approximate tree structure. So it means that at the level of this profile process, you will have something like this. You have a branching event, and then both drop down to 0. But you see also here, we start very high because of this entropic repulsion, and this turns out to be too costly. In other words, these 2 jumps is just a lower order, and then we're back in business because this is first moment squared in both numerator and denominator, so the whole thing converges to 1. Okay, let me say something which I find interesting about this entropic repulsion. It's all about how do you avoid balls, because you see the problem is we have, what's been going on is some sort of dimensional reduction. We start with a 2-dimensional problem. We identified 1-dimensional process, namely this profile process, and it turns out that this 1-dimensional process encodes all the information you need. But if you run Brownian motion, you don't see this profile process. It's something in the it's a meta process which is in the back. But in fact, it does say something interesting, kind of counterintuitive about the way that balls are, the covering happens. And by this I mean the following. So if you take a ball with 0 occupation time, so you run Brownian motion up to time t, and there is somebody which has still 0 occupation time, and you consider its profile process. So this sequence of concentric balls shrinking to the one with zero occupation. Well, we know how the profile process looks like. So you start with a macroscopic ball, and then you record its occupation, and we'll, okay, this is the linear interpolation. Then we'll do something like this. You shrink the ball, and the whole thing goes up, and then you shrink, and it has even larger occupation, and then only at the very end it will go down. But okay, these are some details. So you start with something of order log epsilon, and this is something of order square root of log. But this is counterintuitive because it tells you that you avoid ball by spending lots of time at higher scales, which is maybe not exactly what you would expect. But in order to see that we're talking about extremal events, okay, this is an extremal event, which however, if you bring it to the limits, to the extremes, it does kind of make sense, because it says that Brownian motion is doing something very weird in these regions. And the extreme of this is something like this. Okay, think of Brownian motion wriggling around indefinitely long. Of course, every time you go around it, of course it's not going to be doing something like this, but every time you go around it, you increase the occupation at higher scales, but you still have no occupation at lower scale. Okay. In fact, I mean, this is obviously not what Brownian motion will do, but based on the analogy, which is also emerging from this with the hierarchical field, one can make pretty nice educated guesses at what will happen on Brownian motion. This is based on this work of Chauvin-Rouault for the branch of Brownian motion. It's essentially a natural guess to believe that Brownian motion, when it gets closer to this region with zero occupation time, it's like a Brownian motion in a potential, and this ball acts as a repulsive force. So whenever Brownian motion gets closer, it gets repelled. Okay, so let me say something to sum it up. How do you avoid balls? And so comparing the macroscopic and the microscopic scales. So what I'm trying to do is to bring down to the two papers by Demo Perez Rosenzaituni and the one with David to two sentences about the strategies how you avoid balls. Now, the two papers are it's a highly I think things can get extremely technical and difficult, and the two papers are pretty long. I make the joke. Is over here. I make the joke that if you like to go to the dentist, you should read these two papers. It'll feel just like the same. It's but the ideas behind them is I think it's simple. It's the details which are really difficult. As far as I'm concerned, I would have never been able to do them without David. So I have tremendous respect for all these things. And so what is the strategy we implement the macroscopic scale? Well, you don't go there. You just avoid the regions. Okay. On the other hand, the microscopic scale, you do go there, but you wriggle around. You spend lots of time around it, and you never hit it. And so the two mottos are: don't go there and procrastinate. Okay, so some interesting. So I hope I convince you. So I'm trying to identify numbers, the leading order, the second order correction, but I hope I convince you it's not about numerology. I mean, these numbers have a meaning and about the physical process, what's going on, and of course it's a natural attempt now to improve this picture. Now, based on the analogy which is emerging from with the hierarchical field with branch random walk and branch random motion, it's natural to believe that the cover time without any further correction should be tight, that the fluctuation should be given by a randomly shifted gamma distribution like in the hierarchical field. Of course, the full thing will be probably something very interesting about the extremal process. So remember, the extremal process in this case, it's even I think it's even hard to formulate what exactly the extremal process is, but it's about these orange islands, the regions with zero occupation, and it should be given by a Poisson cluster point process. What do I mean by this? Is something like this: that the center of these islands should be given by Poisson procedure. Just throw them randomly with a certain intensity. But you see, it cannot be the end of the story because there is lots of structure. If you zoom in, you see you have these islands with structure, and these should be the clusters. Now, how to describe this cluster? I think it's a tricky problem. There has been some. I think it's important progress, which is not quite at this level of precision, but I think it's a there's good reason to believe that it's a fundamental step towards this. The description of the cluster is the recent work by Komets, Popov, and Vachkovskaya. There should be some sort of random interlacement in 2 dimensions, which describe these clusters. But as said, I mean, it's a difficult problem. In any case, so there should be that the 2-dimensional covered time is in the universality class of the hierarchical field. There is some reason to believe it. It's probably still a long way to get the full picture. Okay, let me conclude with a last observation about scales. For this, I will go back to the 2-dimensional Gaussian free field, which was this Gaussian field indexed by Z2, and the covariance is given by the Green function. Now, I mentioned this in this talk about multiscale analysis. So if you want to apply this multiscale analysis, you better, it's based on what I was trying to convey. It's based on 3 simple steps, but there is step 0, which is identify the scale first. If you don't have the scales, then there's not much to say. Now, the scales had been identified in a beautiful work by Bolthausen, Deutschel, Giacomin 15 years ago. And at least on the mathematical side, I don't know if in physics, I think there were already some indications, but in any case, so this is what Bolthausen, Deutschel, and Giacomin did. They consider a certain telescopic decomposition, which is the following: is take any site and and the random variable associated to this site. Then consider the random variables which are on this cross, the sigma algebra generated by the random variables on this blue cross, and project these random variables onto the cross. So it's a projection of a Gaussian on Gaussian, so it's going to be a Gaussian random field, a Gaussian random variable, and then it's a telescopic decomposition, so you make it up. You could think, okay, we haven't gained anything. It's exactly rewriting this random variable. In fact, we've gained a lot, because it turns out that this is a common branch. By this, I mean the following. You see, this depends still on the choice of your site. I've chosen this site here, so you could expect that if you choose another one, things will change. They do change, but not much. In this sense, it's a common branch. If I take this other site, or this other site, or this other site, this does not change much. As long it's a difficult problem, then you have to stay away from this boundary. And the problem how to really make sense of what I'm writing to any given level of precision was solved by Branson and Zaitouni with a beautiful homogenization procedure. But in any case, the main idea, the message is this doesn't change much. On the other hand, if you look at this field now, the recenter field, and you consider the restriction indexed by the first quadrant, and then the second quadrant, and the third quadrant, and the fourth quadrant, well, you get 4 independent copies of the Gaussian free field, but on smaller boxes. So there is no reason now that we've seen this to stop here. You can iterate the procedure and consider this decreasing sequence of boxes. And this suggests that behind the 2-dimensional GFF, there is a 4-area hierarchical field. So this is the first step, the second step, the third step, all the way down. It's not exactly, it's approximate, but it's enough close to a hierarchical field for a full analysis of the extremes. Okay, also here there are lots of amazing works, and I would think to believe that what is known today about the two-dimensional GFF is really saying that the two-dimensional GFF is in the universality class of the hierarchical field. It goes from the leading order of the maximum all the way down to the recent work by Biscuit-Bouidot describing the extremal process. So to sum it up, and I will tell you why I think this is an interesting question. So the question of scale. So in the hierarchical field, I believe at first sight one would say, okay, the scales are clear. I see them in front of me. On the other hand, in the cover time, this was this fundamental idea by Demo Perez Rosa Zaitouni. Consider these concentric balls, and these are your scales then. In the GFF, it's about this telescopic decomposition. Now here's the question, is there a procedure to generate scales from first principles without looking at the picture? I think it's an important question in general. Okay, here we understand what's going on. We understand very little in other models, in spin glasses. But the point I'm trying to make is that this one is not really so clear. And by this I mean the following. You see, if I give you the hierarchical field, the scales are clear. But remember, I've told you in order to construct this field, I've told you exactly how big all these edges are. But I don't have to do this. I just can give you the realization of the field. In which case, it's no longer so clear, I guess, at least to me. It is no longer so clear where's the tree. You just see the realization of the tree. So instead of giving, you see, if I give you all this, the energies attached to the edges, I give you 2 to the n plus 1 information, pieces of information. If I give you this, I give you 2 to the n information, which is 2 to the n less. Now, the question, for instance, is how big is the common branch of these 4 leaves? And there is a cute procedure, which is this idea of projecting locally on neighborhood. Now, if you're given a Gaussian field, the covariance induces a metric on the configuration space. So you have a perfectly defined concept of neighborhood. Then I can choose this neighborhood and say, what is the common branch of this neighborhood? Well, it turns out that you can do the following. You can pick any leaf in this neighborhood, and then it turns out that this common branch is just the projection of this leaf onto its neighborhood. Not quite. You're making a small mistake. There's a large number behind this, but the mistake is exponentially small. But you see now, if we have this, we are on track, because this one here is just the whole minus the common branch. If you choose another leaf, it's the whole minus the common branch. So slowly but surely you can reconstruct the tree from the realization of the tree, from the leaves. Okay, so this idea of local projection is construct the tree from the realization of the field. It works smoothly. I mean, it's whether you want to use this decomposition that you get or not. It's another question. But it gives you exactly the tree as we've been using it in cover time on the telescopic decomposition by Bolthausen, Deutsch, and Jacomin. Louis Pierre, I guess, with another kind of procedure, we'll tell you things about the Riemann and the zeta function and other problems. But I wanted to emphasize that there is one big problem, that in these models the scales are somehow trivial. They're not trivial. Well, I mean, we have to agree on the definition of triviality. But one indication is that all these models, branch random walk, cover times, two-dimensional Gaussian free field, they display what is called the Rem freezing transition, which I wanted to briefly mention. I'll mention it for the hierarchical field. Now, if you take the hierarchical field, this is a classical approach from statistical mechanics. The first thing maybe you would like to know is something about the free energy. So it's a sum of overall configuration of these exponential weights. This beta is 1 over the temperature. Okay, in order to normalize, you take the log and divide by at least by the size of the system. Now, this is of course a random function, but we know in the limit of large scales it converges to a deterministic function which has a phase transition. And what we are interested in since we're interested in the extremes, we're interested in the low temperature phase and the so-called spin glass phase. And there things are somewhat shocking. You see this function Okay, so this is of course a fundamental work by the Reed and Spohn on directed polymer Cayley trees. But you see there is something which is puzzling, namely that as long as you're greater than this BC was the leading order of the maximum, then this function is constant. It means that you have the same tree, same one and only tree for all temperature below this BC. And in fact the tree is even there is even a bigger triviality, namely the tree is okay, these models are in the so-called one-step replica symmetry breaking class, and I think Olivier will discuss things from this spin glass point of view. There is another model which is not in the 1RSB class. Of course, it's a famous model. Is the SK model. So you take Ising spins, so a chain of atoms. Then you consider independent Gaussians, this Gij, which will provide some sort of interaction between the spins, and then you consider this Hamiltonian. So it's a Curie-Weiss Hamiltonian, but the two-point interaction is modulated by this Gij. Now you have 2 to the n configurations, just like in the hierarchical field, and this is a Gaussian field indexed by these spins. Now the Parisi ultrametricity conjecture is almost 78 years old, 40 years old. It predicts a different set of scales and trees for different beta. So, say for beta larger than 1, in this case we know it's 1, the transition into the abyss of the spin glass phase. You have a tree which looks completely different depending on the choice of your beta. And even more so, the tree standing behind it is an infinite tree, which is not the case in this Gaussian hierarchical field and cover times and Gaussian free field. Now I call it a conjecture because what I will state here is still a conjecture, but of course there has been amazing progress done by on this Shenton-Kirkpatrick model by Eisenman, Aufinger, who is also here, Louis Pierre, Veiko Chen, Francesco Guerra, Dimitri Panchenko, and Talagro, and other contribution. But still, despite this big progress, this problem, namely, if you take the Hamiltonian of this Gaussian, if you take this Gaussian field and you should multiply by beta and consider the statistical mechanics problem associated to it, there should be, according to the Parisi theory, there should be a procedure which generates, given beta and given the disorder, a tree. Now, this procedure is still nowhere in sight. I mean, we have learned a lot by this series of works I mentioned by these people. We have known a lot that the Parisi theory is likely is somehow correct, but we still don't have a simple way to generate trees. And to conclude, why do I think it's an important question? Because I try to convey this feeling. If you have a tree, we know what to do. But as long as we don't see the tree, we're just like, okay, I think I'll stop here.
Is barrier in your cover time thing? Can you really choose a straight line?
The barrier, yeah. Okay, it's a step by step. I mean, you choose a straight line. You try to get some information, and then in fact you try to but you shift it, right? You shift it down. It's not the right thing. I mean, it's the best thing would be to choose this, what we called in paper with the Louis Pierre and Anton Bouvier, the entropic envelope. Just go for what you expect to see at the end. And then if you do this, you get more information about, you see, the analysis here with David only covers this second order correction. If you want more, you should be able to say something better about these things. It's a very difficult problem because in case of Gaussian fields, we can do explicit computation. Here it's much harder.
What about P-spin spin glasses? There it shouldn't be infinitely RSB, right? It should be easier. Indeed.
It's a good point. I don't believe so in the end. If you really want to have something concrete, it could very well be that there is. So you see, in this case, if you want to analyze, let's say even the hierarchical field, if you want to analyze it by second moment, which is I think is the most concrete way to you have to know exactly the full tree. Then at the end, it collapses to a one scale tree. Now, if you want to apply some sort of constructive way to this to this P spin, I think they are misleading. It might very well be that well, it is so. The tree in the end turns out to be one RSB. But if you really want to get a handle on this thing, then I do believe that there is an infinite tree which simply then collapses in the end. Just like in the hierarchical field. If you see so far these P-spin models, they've been solved by completely different methods, which still leave open questions, which are seemingly very important.
Is the probability distribution of this maximum function for the random walk known, or
For
the maximum function that you're looking at for the random walk? Is there probability distribution as n varies with time? Is the probability distribution known?
This is a good question. I don't know.
Then you could just work out the probability of crossing the barrier.
Yeah, you can. I mean, there are many ways. Let's say, at least in the Gaussian case, to see that the probability is 1 over n. It's not even depending on the Gaussian nature. It has something to do with the rotation invariance of the increments of the bridge. If you want to prove, let's say, go beyond the leading order of 1 over n, or get a better handle on this. For instance, if you stay below this entropic curve, this square root curve, you can proceed by Girsanov, get rid of this curve. Whether the maximum, well, I think the maximum is no, but the law of the maximum of random bridge, that's what you're asking.
The maximum of the n
Yeah.
steps of the random walk, right? You've got a random walk, and then xn is the nth step, and you want to work out the maximum of the first, second up to the nth step.
Yeah,
Probability distribution of that.
I personally not so familiar with these things, but
Reflection principle gives you the distribution of the maximum, no?
But does
Maximum and endpoint together.
yeah, that's a good observation.
So what is known about the maximum of the Sherrington-Kirkpatrick field?
The leading order is known. The free energy has been computed by Guerre and Talagron. There is now a new proof by Panchenko, and I think also Tukai. I guess you have results on this. Now, if you have the free energy, you let beta to infinity, it converges to the leading order of the maximum. But it should be a completely different world. This maximum, as far as I understand, should have anomalous fluctuations. So it's let's say very little is known. Yeah. Sorry.
Anomalous? How anomalous?
For instance, you know the maximum of the Gaussian hierarchical field, you shift it by its level, and then that's tight. In SK, even if you shift it by the maximum, then you should rescale by something of order n to the alpha or something. And the physicists have a complete description. I mean, they have amazing guesses about all these things, but rigorously, I don't know that there is more than the leading order known. And even the leading order, you know, it's a tricky object because it's the free energy solution of a complicated functional related to an infinite dimensional problem with a partial differential equation appearing, and then you take the limit of beta going to infinity. It's a disaster. Yeah.
Yeah, just a comment that to see that SK is really hard is at the first moment gives the wrong answer.
Say it
The
again.
first moment gives the wrong answer for the maximum.
For the maximum.
Yes.
Ah, yeah.
At the leading order, not at the second order. At the leading order, gives the wrong answer.
Yeah, that's
Just a word of caution.
Okay, so maybe it's time to stop it there, and so we'll be back at 11:30 for the next talk. So thank you.